Hi, chemistry students. This is your lesson on mass, stoichiometry, and more. Be sure you have your guided notes nearby and a calculator. As we work through these three examples, please be sure you pause the video frequently as you write them down and also try them out in your calculator. So, as we know from previous lessons, coefficients represent particles and moles. They do not directly represent grams and mass. Here's an example. For example, in the equation for the synthesis of water, you can see that 2 molecules or 2 moles of H2O plus 1 molecule or 1 mole of oxygen gives you 2 molecules or 2 moles of H2O. However, because oxygen atoms and hydrogen atoms have different masses, that's the equivalent of 4 grams of hydrogen plus 32 grams of oxygen to give us 36 grams of water. Now, again, there is conservation of mass, as you can see, but you can also see that the coefficients represent the moles and not the grams. So let's try a couple of examples of stoichiometry problems where we have to use grams. So in a stoichiometry problem, one that is practically used in a laboratory, someone probably is saying to you, I want a certain amount in grams of a product. And you have to determine the starting ingredients and how much you need of each. And generally, you're going to do that in grams. You're not going to count out particles. You're going to weigh out amounts. So you're going to have to convert things into moles. So the steps in a really practical chemistry stoichiometry problem are the following. First, you have to have an equation. You're doing a reaction. You have to have an equation, and that equation has to be balanced. Then you're going to be given an amount, probably in grams, and before you can use that balanced equation, you're going to convert the given units to moles. Once you have converted the given units to moles, then you can use your recipe, your balanced equation, and you'll set up a mole ratio to convert moles of what you were given to moles of what the client wants. All right. Now, once you know moles of what the client wants, the moles of the wanted, you can then convert back to moles of the wanted to the desired unit. Now, this is going to make a lot more sense as we work through some examples. So let's try a couple of examples to see what I mean. Now, just as reference for each one of these steps, this is the most practical stoichiometry problem. Generally, you're given a mass and in grams, and you're going to want to know a mass also in grams. And then you're going to need a balanced relationship between two quantities in a chemical equation, in a chemical reaction. We can only do this 2 quantities at a time. So there'll be a given quantity and a wanted quantity, and you will pick them out. And so, for example, if I say I have a certain amount to begin with, and your client says, well, how much of the product can you make from that? That's what you'll be calculating. And you're going to need a balanced equation so you can use the coefficients. So the first step is the balanced equation. Then you're going to say, okay, let me go back to my storeroom. Let me see how much of the starting ingredient I have. It'll be a mass. Before you can use the equation, you'll have to convert that mass of given into moles. So you do that with a division. You divide by the molar mass, and that's what this dimensional analysis term means, because since mass is on the bottom, it'll be a division. That'll give you the moles of what you were given. Then you're trying to figure out, well, how much can I give him of what he wants? So there's my starting ingredient. Here's our mole ratio. We're able to pull that down directly from the equation and cancel factors to get moles of what we want. But since most people don't speak in moles, they speak in grams, we'll have to convert moles of what we want to grams of what we want by multiplying by the molar mass of that thing to get the mass. All right, let's try a few examples. Oh, and I wanted to just show you this as well. Now, usually this is the most practical, the center road. Usually weigh something out, you figure it out, you are able to tell the client grams of how much he wants of the product. But you could also, if you're working with gases, it might be more practical to talk about volume. Or if you're in a chemistry class where the teacher really wants you to use your exponent key, you will be doing molecules. But each one is just a mole conversion to mole ratio back to a conversion to the unit that you want. All right, so we're going to look at an example using something called the thermite reaction. Thermite reaction is a highly exothermic reaction between rust, iron 3 oxide, and powdered aluminum. And if you give it just, and it's weird because it's a single replacement, but it's not done in solution. You actually just mix these two powdered materials together and ignite them, give them a little bit of activation energy from a little magnesium strip that has been lit. And it's very exothermic, and its product is molten iron. So it's used a lot of times, this thermite reaction, in welds. So let's take a look at it. This is a short video from the North Carolina School of Science.
We will use a thermite reaction as an example of a very exothermic reaction. The thermite mixture consists of iron 3 oxide and aluminum powder. A small piece of magnesium ribbon is used as an igniter. The reaction is extremely exothermic. It is an oxidation-reduction reaction between the aluminum and the iron plus 3 ion. The iron plus 3 ion is reduced by the aluminum to iron metal. The reaction is so exothermic that the iron is melted and drips through the bottom of the flower pot. The melting point of iron is about 1500 degrees Celsius.
So again, here's the equation. You can see it's very exothermic. It's a negative delta H. And there you go. So let's do some stoichiometry using this process of thermite. Okay. So if you go through your 4 steps, you first need a balanced equation, which is right here. Iron 3 oxide plus aluminum gives us iron and aluminum oxide, and you can see it's a 1:2 to 2:1 ratio. Now, we can only talk about 2 terms in here, and here's our problem. How many grams of aluminum are needed to completely react with 135 grams of iron 3 oxide? So we want to be very efficient. We have put 135 grams of iron 3 oxide in our flower pot, and we want to know the exact amount of aluminum we need to put in there for them to completely react with each other to give us this molten iron. So we're going to identify our given, which is 135 grams of iron 3 oxide, and our wanted is grams of aluminum. Those are the 2 terms we're trying to get to. So again, I've got the steps written out here. So in order to travel from grams of iron 3 oxide to grams of aluminum, we have to go through these 3 steps. In order to use the balanced equation that we have as step 1, we have to change grams of iron 3 oxide to moles, okay? Because again, iron 3 oxide and aluminum have different masses. It's not a 2:1 based on mass, it's a 2:1 based on moles. So step 2 is to convert to moles. To do that, we have to have the molar mass of iron 3 oxide. Yeah, these are very long problems, guys. So molar mass of iron 3 oxide, we calculate. Remember, you go at least out to the hundredths place. So the molar mass of iron 3 oxide is 159.70 grams. So our first step here is to divide 135 grams by 159.7. We're converting it to moles. That is 0.845 moles of iron 3 oxide. Now, in your calculator, don't re-enter it. Just leave it as is. It probably goes out a lot. We do not round in these stoichiometry problems till the end. This parentheses there is just to keep track of it for you as we learn the process. So at this point, we have converted grams of iron 3 oxide to moles of iron 3 oxide. And so instead of our recipe being 1:2, we're basically saying we don't start with 1 mole of iron 3 oxide. We start with 0.845 moles of iron 3 oxide. So how many moles of aluminum are we going to need? That's our next step with the mole ratio step. Okay, so we identify the 2 factors from the equation that we're using, and we put on the top of the dimensional analysis here on the numerator the thing that we want, which is aluminum, and on the bottom the thing that we were given, which is the iron 3 oxide. We pull it down exactly from the equation. So essentially what we're doing is that we're taking this 0.845 moles of Fe2O3 and we're multiplying by 2. That's going to give us 1.69 moles of aluminum. Think about that in the equation. So instead of being 1:2, it's 0.845 to 1.69, where they would completely react. But again, we have to go back to the problem and see it says how many grams of aluminum are needed. So we know moles of aluminum. We now have to go and convert to grams of aluminum. At that point, we're going to look up the molar mass of aluminum on the periodic table, which is 26.98, and we'll have to multiply by 26.98 those 1.69 moles of aluminum, which we do, and we get 45.6 grams of aluminum. So if I were going to mix up this thermite reaction and hope that everything would react and there'd be nothing left over, I'd put 135 grams of rust, basically, mixed in with 45.6 grams of powdered aluminum, ignite it with the magnesium, and we would get a certain amount of iron, but we would not be wasting any of the ingredients. Now, again, we rounded to 3 significant figures because this has 3 significant figures. And in multiplication, we round to the least number of significant figures. Now, you might be asking about these 1s and 2s and 1s. Those are exact numbers because they represent ratios or amounts, equivalences, conversion units. This one has 5, this one has 4, this one has 3. Those are rounded numbers that account for significant figures. So our answer will have 3 significant figures, which is 45.6 grams. Okay, let's try another one. In this example, it says how many grams of copper can be produced by 4.55 grams of aluminum when it reacts with excess copper chloride to form copper and aluminum chloride. Wow, that's a lot of words. Well, let's kind of just start at the beginning. We need to have a balanced equation. So we need to look at this and decide what the balanced equation is. Here's the skeleton. It says that aluminum reacts with copper chloride to form copper and aluminum chloride. Now, once we have the skeleton, we'll need to balance it, which we do here. It's another one of those 2 to 3 to 3 to 2 ratios. Now we got to figure out what the given and the wanted is. And there are a lot of words in here. I want you to notice what has the number and what has the how many. And everything else is just gobbledygook to confuse you. Sorry about that. So we're getting rid of, so how many grams, there's our how many. Here's our number, that's our given. And all this stuff about when it reacts with excess, we don't care about the excess reactant and to form, and we're not asking about the products this time. So we're asking about the copper and the aluminum. We're not asking about these particular things. We're asking about the copper, but we're not asking about it in terms of this clause here. We really want to get it down to the clause where we see the how many and the number, the given. So we're going to get that set up. So here's our given. Our given is 4.55. How many grams of copper can be produced by 4.55 grams of aluminum? So we're given 4.55 and we're trying to get to grams of copper. So this is truly somebody saying, hey, I got 4.55 grams of aluminum. How much copper can you give me? Okay. Now we're going to need the molar masses from the periodic table of the aluminum and copper. So I put them here. We're going to have to set it up. 4.55 grams of aluminum equals how many grams of copper. Now we're going to do each of the steps from the starting with the balanced equation and us setting it up. We need to change grams of aluminum because it's not 2 grams to 3 grams. It's 2 moles to 3 moles. So we have to convert this to moles. We'll do that by dividing by the molar mass. That would give us 0.168 moles of aluminum. So instead of 2, like this is just figuring out a recipe. Instead of 2, we have 0.168 moles. And we want to know how many moles of copper that would give us. Our ratio, and we take that from the 2 terms in the equation. On the numerator, we put the thing that we want. The denominator is the thing we're trying to cancel. So it's going to be 0.168 moles times 3 divided by 2. That means we're going to be able to produce 0.253 moles of copper. So again, instead of being 2 to 3, it's 0.168 to 0.253. That's the same ratio. But our client doesn't talk in moles. They want to know how many grams of copper. So the final step is a multiplication where we convert to grams using the molar mass of the copper. So we multiply. And again, once we've done all this, we just leave it on our calculator. 4.55 divided by 26.98 times 3 divided by 2 times 63.55 gives us 16.1 grams of copper. Try it yourself. Make sure you can get this answer as well. All right, now example 3 is one of those annoying ones where we don't go through this middle road of just grams to grams, but we pick a different kind of starting unit and ending unit. This one in particular is going from volume to molecules. So the example says how many liters at STP of ammonia will be produced from 1.24 times 10 to the 25th molecules of H2 at STP. So the given here is in molecules, 1.204 times 10 to the 25th molecules of H2. And remember, 1 mole of molecules, MC is what I usually write for molecules, 1 mole is 6.02 times 10 to the 23rd molecules. We're converting to liters, and remember, the relationship between moles and liters is 1 mole is 22.4 liters. Now we're going to need step 1, the balanced equation. So the balanced equation for the synthesis of ammonia is going to be 1 mole of nitrogen plus 3 moles of hydrogen to give us 2 moles of ammonia. Again, we'll set up our given and our wanted. Here's our given, 1.204 times 10 to the 25th molecules of H2. Here's our wanted, how many liters of ammonia? And again, at STP. So remember, step 2 is to convert to moles of hydrogen. Step 3 is to do our mole ratio in order to get to moles of ammonia. And step 4 is to convert moles of ammonia to liters of ammonia. So here's step 2. We're going to divide 1.204 times 10 to the 25th molecules of hydrogen by 6.02 times 10 to the 23rd molecules. That's going to give us basically 20 moles of hydrogen. And then we're going to use our mole ratio. So the mole ratio from the equation up here is 2 to 3, 2 ammonia for every 3 hydrogen. So our 20 moles of hydrogen, so instead of being 3 to 2, it's going to be 20 to something. It's going to be a 2 to 3 ratio. So we're going to multiply 20 times 2 and divide it by 3, and that'll give us 13.3 moles of ammonia. And then we have to convert to liters. And again, notice factors cancel. The only thing that is left is going to be this last factor on the top of the denominator of step 4, 22.4 liters. Again, moles cancel, hydrogen cancels, molecules cancel, and we're left with 299 liters of NH3. And that's your example 3. Now, the only way to get good at this is just to keep practicing. In this lesson, you're going to try one, you're going to do some homework, and I'm going to direct you to some of the helpful videos for even more examples that are done for you.